Okay, so a problem I meant to put a video up on because no one really quite got it right was problem 2C in homework 4. And that is for f and g and L2, prove that the convolution, which makes perfect sense as an L-affinity function, is in fact the inverse Fourier transform of f hat times g hat. Okay, and this is a good problem to do because when you deal with Fourier transforms for L2 functions, you really do have to be careful that you're taking the Fourier transform of something that makes sense. And you're carefully doing things because the Fourier transform for an L2 function is a limit, period. It's the limit definition. So let's see how to do this. Okay, so let's go to the whiteboard. Okay, so right, so first of all, let's pick Gn. So let me make this black here. All right, so so let's say we have Fn, Gn, and L1 intersect L2. I mean, we can even take it to be Short's functions. We could take it to be C infinity with compact support, whatever. This is enough, actually. So if we're going to take the Fourier transform in f and g, we, so remember what that is. It's even, well, let's say Fn converges to f, and Gn converges to, well, not f, but g, and L2. Right, so remember f hat is this L2 function. The limit of fn hat, excuse me. Sorry about that. And g hat is this limit here. Okay, so a note is that, well, I claim that Fn convolved with Gn converges to F convolved with G uniformly. Let's do that in the L infinity norm. There's not a whole lot to that. It might really be so easy that it doesn't really require much much discussion, but I'll just write the details out. Right, so this is going to be, just do triangle inequality and linearity. F convolved with G, F convolved with Gn. Try to squeeze it here, F convolved with Gn. And then let's do Fn. Try and do that. It's not very intelligent. So I'll do it right here. F convolved with Gn. Fn convolved with Gn of x. Okay, so right, so we can basically write this as one integral, first one. Right, using linearity, this is going to be integral f of x minus y, g of y minus gn of y. And this is going to be, well, over r, whatever, rd, rn, whatever. And so this is going to be, so let's see. Right, so this is really going to be, well, we have a common gn here, so it's going to be Fn of x minus y minus Fn of, minus f of x minus y times g Gn or G? It is Gn. Okay, well, just smash in absolute values. So yeah, so just smash in absolute values everywhere. We have that what I had before is less than or equal to this thing right here. Not very subtle. And use Cauchy-Schwarz. This is going to be less than or equal to the L2 norm of F, L2 norm of G minus Gn, plus the L2 norm of Fn minus F, L2 norm of Gn, well, this goes to 0 as n goes to infinity. This goes to 0 as n goes to infinity. And this goes to, well, the L2 norm of G. So in particular, it's finite. And remember, F and G are L2 functions. All right, so this goes to 0 as n goes to 0. Okay. So F convolved with G, this was independent of X. Okay, so right. Okay, so in particular, right, so F convolved with G is going to be this limit in L infinity of Fn convolved with Gn. Okay. Okay, so so first of all, let me make a comment here. So you can use Young's inequality here, or don't really need that. So F and G are an L1, sorry, Fn and Gn are an L1, and they're an L2. So in particular, Fn convolved with Gn. Let me just get the pen here. Get rid of this. Right, so particularly Fn Gn is an L infinity, and Fn Gn is an L1. Okay. Because Fn and Gn, they're all, everything is an L2, L1 intersect L2. Okay. All right, so what's the punchline here? If we have something that's an L1 intersect L infinity, it's trivially an L2. Why? Well, let's just, I mean, there's really not a whole lot to this. Right. Fn convolved with Gn squared, Rd, whatever. Well, this is just multiplied by itself. It's multiplied by itself. So pull out the L infinity norm of one of them. So I wasn't kidding. This is really not anything deep. Okay, so this is the L infinity norm. And the whole point is that we want to use one of the, we want to use what we proved, or we want to use B, and we want to use Fourier inversion. And we want to just carefully check that we can do that. Okay. I think that's what people, I mean, most people have the right idea, but you really want to be careful and check what you can do. Okay, so this is an L infinity, but this whole thing here for each n is an L1 intersect L2. So in particular, well, it's in really, yeah, we don't really care about that. We just care that it's an L2. So that Fourier inversion is true. All right. So in particular, as L2 functions, Fn convolved with Gn is Fourier transform of Fn convolved with Gn times the inverse Fourier transform. Okay, that's just Fourier inversion. We know Fourier inversion holds for L2 functions. All right, so let's go back a second to the PDF. Okay, right, but F1 and Fn and Gn are an L1, so we can apply B to Fn and Gn. All right, so let's do exactly that. Back to the whiteboard. All right, so I'm going to get rid of all this here because that was just to show that this is an L2. So I'll get rid of all this. I wish the Adobe Reader eraser was this nice. But anyway. Okay. Right. So this is going to be equal to. Yeah, it has nothing to do with limits or anything. It's just that Fn and Gn are L1 functions. So this is going to be Fn hat Gn hat inverse Fourier transform. Okay, now we just need to be, again, we need to be a little careful. So, right, so Fn, in particular, Fn hat is an L2. Well, sorry. So Fn converges to F hat in L2. Gn hat converges to G hat in L2. Okay. So what does that mean? By just Cauchy-Schwarz inequality, like you've probably done many, many times, this converges to F hat G hat in L1. Okay. Okay, so that implies, because we have L1 convergence, that implies that the inverse Fourier transform of F hat Gn hat, okay, that converges to the inverse Fourier transform Fn, oops. Right, and I should say also, well, I'll make a comment in a second. What am I doing? Right. So remember, well, we just that was part, super easy part of the homework. I think, yeah, we actually wasn't homework. We've done it in lecture many, many, many times. That in general, whoops, sorry about that. Do anything there. So in general, Fourier transform, inverse Fourier transform, same thing except plugging in minus x instead of x. Yeah, so remember this is, well, let's do it like this in case you forgot, which you probably shouldn't, but Right, so the inverse Fourier transform, that. So this is going to be d f of y e to the, so this is going to be inverse Fourier transform, so it's positive. No, it's a minus, no, it's positive. I always forget minuses versus positive. Not very important, but it's important to know one's positive, one's negative. That's really all that freaking matters. Anyway, so yeah, smash in absolute values is trivial, and this should be big F. So. Okay, so the L infinity norm of the Fourier transform is less than or equal to the L1 norm of the function. So if we have convergence in L1, then we have convergence in L infinity. And this is there's nothing wishy-washy. In particular, because Fn, well, it's an L1 intersect L2, so the Fourier transform is an L2. And so because this is an L2, this is an L2, the whole thing itself is an L1. So in particular, the inverse Fourier transform is just the integral. It is literally just the integral for L1 functions. It is exactly, it's exactly just the Fourier transform with a minus plugged in. That's really the definition of the inverse Fourier transform for an L1 when we have an L1 function. Okay, yeah. So that basically proves it. If you go back, yeah, so in L infinity, we have equality here. We go down here using Fourier, Fourier inversion. And I guess if there's concern about this inverse Fourier transform, well, so yeah, this is convolution is an L1. Well, the convolution again is an L1 because, well, that was the L1. Yeah, Fn and Gn are an L1, so Fn convolved with Fn convolved with Gn is an L1. So this is an L2 intersect L1. We proved before that's an L2 because it's an L1 intersect L infinity. So in particular, the Fourier transform and the inverse Fourier transform are just integrals. And you have Fourier inversion for L1 intersect L2 using integrals. You don't have to do any of this funny business of Fourier transform is a limit of other Fourier transforms. Okay, so maybe I should have made that clear if I didn't, if that wasn't clear. Right, so yeah, so this inverse Fourier transform throughout is an integral. This literally means here the inverse Fourier transform integral. And so, yeah, and so that finishes the proof. That takes care of, yeah, all these convergencies are in L infinity. So, you know, this function here as an L infinity function has no choice but to be this function as an L infinity function, and hence they're equal almost everywhere, which is exactly what I wanted you to prove. So it's a little tricky, but I think it's good to let this soak in, and it's good to understand it. Anyway, all right, so hopefully that helped. Yeah, so long, take care. We're almost done, so just hang in tight. Bye-bye.